I'm Jackson Morris. I'm a grad student at UCSD. Yeah, I guess I should say thank you very much for having me. I really do enjoy these quantum meets on YouTube, so it's nice to participate again. Yeah, so today I'm going to be talking about this recent work with Daniel Greer, who's my advisor, and with Kevin Wu, who's at the IAS, but he'll be joining Caltech in the fall. And this paper is titled QAC0 contains TC0 with many copies of the input, which might just look like alphabet soup for now, but hopefully in a few minutes I'll have defined all of these terms and sort of what I mean here by with many copies of the input. So let's get started. Okay, so the setting for everything I'm going to be talking about today is going to be constant depth circuits. So on the left here, I have some classical circuit consisting of AND gates. And in case you haven't seen this before, the depth of a classical circuit is just the sort of like maximum path length between any input and this one like designated output wire. And so, as you can see, I've sort of divvied it up here into D many layers. And then on the right, of course, we have a quantum circuit, and we sort of have a similar notion of depth, which is just the total number of layers of non-overlapping gates in our quantum circuit. And so for today's talk, we're going to be interested in both cases where the depth of our circuits is some fixed constant. Or rather, we have a family of circuits, one for every input size, and the depth of any circuit in these families should be bounded above by some constants. So in other words, the depth does not scale with the input size. Okay, so now I guess I'm going to give like maybe a brief history and a couple of motivations for why one might want to study these constant depth quantum circuits. The first is that some recent work and some older work has shown that shallow circuits with large entangling gates, like either fan-out or large Toffoli gates, might be physically realizable in the near term. So that is to say that the constant depth part is sort of to be expected just because of low coherence times in like existing quantum computers, but the large gates part is sort of new in that experimentalists seem to be able to have these gates as sort of native, these large entangling gates as native gates. The second reason to study the circuits is that they might provide us some examples of quantum advantage. So in particular, there's this pretty recent line of work initiated by Bravi, Gossett, and Koenig in 2017, and then Benny Watts, Kothari, Schaefer, and Tal in 2019, where in both cases they give some search problem, meaning one input and potentially many correct outputs, that is solvable by a constant depth quantum circuit, but is very far from being solvable by a constant depth classical circuit. So they prove super strong lower bounds against sort of the analogous model of classical computation for the same task, right? And the sort of final reason is, I guess, more of an intrinsic complexity theoretic motivation for studying these circuits, is that in the classical world, people have studied and some understanding, at least, of the sort of landscape of what these sort of classical circuits can do. So in particular, in the 80s and 90s, there was a large number of works, I guess, first showing that AC0 can't compute parity, and then showing that AC0 with parity gates can't compute mod 3, for example. And so a lot of really nice techniques were developed, including random restrictions and polynomial methods, some like very beautiful mathematics to sort of deal with these increasingly powerful constant depth circuit models. And okay, while progress in classical circuit complexity has sort of stalled in the years since, we are very far from being able to say we have as good an understanding of the sort of analogous quantum models. Right. So on the previous slide, I mentioned the search separation exhibited by Bravy, Gossett, and Koenig, and then later improved by Benny, Watts, Kotarny, Schaefer, and Tall. And so in case you haven't seen something like this before, when I say a search problem, it just means that for any fixed input, there are potentially many correct outputs. So I just have some toy example here where we're given some n-bit string x, and we're asked to return an index I such that the ith bit of x is equal to 1. And so this is sort of different from the usual notion of a decision problem that we like to think about in computer science, where we're just asked to produce a single bit of output for any given input. And so, yeah, so just to make formal, what Bravy, Gossett, and Koenig show is they show that there is some search problem that can be exactly solved, perfectly solved on all instances by a constant depth quantum circuit, aka a QNC0 circuit, which is some circuit that consists only of 1 and 2 qubit gates. But they show that the same problem can't be solved with probability, say, better than a half on average by constant depth classical circuits consisting just of 1 and 2 bit gates. So think and, or, and also not gates. And so potentially one question you might want to ask upon seeing this result is, okay, we have a search separation between these two classes, but can we find a decision problem to separate QNC0 from NC0? And in some sense,
the light cone argument forbid this, like, because I thought you could always
right. You've exactly predicted what comes next. Yeah.
Okay. Cool.
Right. I guess what I'd like to say is, like, obtaining a decision problem, finding a decision problem to separate these classes would in some sense be a stronger separation than a search separation. But as Atul mentioned, this is a fool's errand. There is no decision problem to separate QNC0 from NC0. And this just follows from a relatively standard light cone argument, but it's so quick, I think I'll just go through it really fast. So to see this, suppose we have a constant depth classical circuit computing some Boolean function f. If the circuit has depth d, then what we can do is we can start at the output node, or the output wire of this circuit, and sort of just trace backwards. And every time we encounter a gate that touches this wire, we pick up the wires that fed into that gate. And so we have this growing collection of wires as we traverse backwards through the circuit. But in NC0, the fan-n is bounded, meaning that the number of wires going into any gate is at most 2. So every time we encounter a new gate in this process, we grow the number of wires we have by at most a factor of 2. And so at the very end, we're going to be left with some set of input bits that could have possibly affected this output bit. But since d is constant, 2 to the d will also be constant, meaning that this function is just some local function. It depends on only constantly many input bits. However, the sort of exact same reasoning applies to a quantum circuit, which only consists of 1 and 2 qubit gates. So as you can see here, we let's just say our circuit gate set is C0, and then any choice of single qubit gates we like. Well, the single qubit gates aren't really going to grow our light cone, so every time we hit a C0, we're going to at most double the number of wires in our sort of light cone as we go backwards through the circuit. And so at the very end, we're going to again be left with just some constant number, 2 to the d, many inputs at most that could have possibly affected our output. And so sort of by this reasoning, the set of functions computable in these classes is the exact same. And so what this means is, in order to obtain a decision separation, we need to turn to stronger models of computation. So in particular, we're going to upgrade our quantum circuit model to QAC0, which I'll define now.
Sorry, can I ask a small silly question? So I know it is the case that one wants a decision separation in general, and it's considered to be more powerful than a search separation. But is there like why is that? Like, what is like? I also intuitively think that's the case because we know many more search separations than we know decision separations. But is there like some formal reason for why that is the case, or is there some way to think about it?
I think one formal way in which search separations are like more desirable than in which decision separations are stronger than search separations is you can always view a decision problem as sort of as a search problem where the output space is just 0, 1.
Okay.
Yeah.
Okay.
So like decision problems are in some sense the hardest search problems.
I see. Makes sense. Okay, thank you.
Yeah, sure. Right. So now I'll define some new models of computation. So first, AC0 circuits are classical circuits, again of constant depth and polynomial size. But I guess I should mention that whenever I say size, I just mean the total number of gates in a circuit. And these AC0 circuits are going to consist of and OR gates like before, except we're no longer going to have this restriction that the number of wires going into any gates is bounded, aka these circuits have unbounded fan-in. So I've drawn some circuit here that has and OR gates and constant depth. Now QAC0 is a class that is meant to be something of a quantum analog of AC0. Again, these are going to be constant depth quantum circuits of polynomial size. But now they can consist of so-called quantum AND gates and arbitrary single qubit gates. And additionally, we allow for polynomially many ancilla qubits. As I've drawn here, we have some QAC0 circuit acting on input X with 0 to the A at the bottom here, indicating the sort of ancilla or workspace qubits. And we require for this workspace to be polynomial size. Just to be very precise, when I say a quantum AND gate here, this is sometimes referred to as a large Toffoli gate or a generalized Toffoli gate. But this is a gate that acts on n+1 qubits just by XORing the AND function of the first n bits into the final qubit. Okay. However, there's sort of the one subtle difference, I suppose, in the definitions of these two classes that doesn't exactly make them apples to apples, and that is in AC0 we're allowed unbounded fan out, meaning that the number of wires outgoing from any gate can be as large as we want. But a priori this is sort of not allowed in QAC0. I'll explain why in a second. Are these definitions clear? Any questions? Great. Before I get to why that subtle difference is there, I'll first talk about what we know about QAC0. So this class was first defined by Moore in 1999, and one of the things he shows in that work about QAC0 is that the following three tasks are all QAC0 equivalent, meaning that if you had a QAC0 circuit that did one of these tasks, you could then bootstrap it into another QAC0 circuit that did any other of these tasks. And in particular, these tasks are computing the parity of n bits, preparing the n-qubit cat state, and implementing fan-out on n qubits, which I haven't defined yet, but this is it. So like I said, classically fan-out is this thing. It's not really an operation. It's just taking the result of a gates evaluation and plugging it into some large number of gates further down in your circuit. And so quantumly, we can't really copy information. And in particular, we need for things to be reversible. So we define this quantum fan-out operation as taking a bit and simultaneously XORing it onto n other registers. And so you can sort of think of this as like a deep C0 circuit or something, where all of the C0s have the same control but different targets. And so what more proves is that implementing this gate is the same as preparing an n-qubit GHZ state or a cat state, and it's also equivalent to computing the parity function. Right. And I guess another result I'd like to mention is that this fan-out gate is also very powerful in the sense that it allows you to compute even harder Boolean functions than parity. So for example, with the fan-out gate, you can construct a constant depth quantum circuit, aka a QNC0 with fan-out circuit, denoted here QNC0 WF, that computes majority or mod p for any prime, or you can even implement the quantum Fourier transform in constant depth with fan-out. And so this is a bit strange because classically, fan-out doesn't really seem to give us any sort of crazy power like it does in the quantum case. And so, right, all this to say that computing parity or implementing fan-out are sort of very strong quantum operations, and that they lead to all of these other consequences. And moreover, all of our classical lower bounds still hold even in the presence of unbounded fan-out. And so this is sort of an important difference between these constant depth classical and quantum circuits. Oh yeah. Question?
Hi. So I'm just trying to understand something. So in QAC0, you don't allow mid-circuit measurements, right? But if I were to allow them, you could allow. So I could do a measurement and then do like a classical fan-out, right, in the circuit, and then I suppose that would allow me to create quantum fan-outs, right?
Yeah.
Or no? Is that equivalent or not? I guess I'm trying to understand how does the power of fan-out compare to the power of doing mid-circuit measurements in a sense. But
yeah, that's a good question. I believe mid-circuit measurements should let you compute all of the things shown here, but I'm not sure if it goes through the route of like implementing quantum fan-out. It might be the case, but I know there was one paper showing that QAC0 with mid-circuit measurements lets you compute some hard functions, but I can't remember exactly how that construction works.
Okay.
Yeah.
Thank you.
Okay, and now that we've already interrupted, I'll ask one quick question, which was that so you I think sort of were trying to motivate that certain non-local gates can be applied in certain architectures. Do we have any reason to believe that these fan-out gates also have in some architectures some native implementation, or we just believe that it's sort of difficult in general?
So this is a good question. I'm not a total expert on what's going on in the experimental world, but what I do know is that at least with neutral atoms, there is some sort of global entangling operation they can do that looks a bit like fan-out. And so I believe it looks like a large tensor product of swaps.
I see.
But yeah, I don't know about the details.
I see. Okay, thank you.
Yeah. Oh, and I guess there's also some work suggesting that in trapped ion quantum computers, you will be able to do fan-out natively, or at least someone has been able to. So yeah, that's sort of where things stand. But yeah.
Okay, thank you.
Maybe take that with a grain of salt. Yeah. Okay, so right.
Very like a trivial question, but like just for clarity, can you explain what is the classical fan out? Like, is it just like doing ANDs of all the bits? Like, is the Toffoli gate and classical fan out same things?
No, not exactly. So right. So I had, let's see, this circuit here. Oh, actually, no. Let me go here. So this circuit isn't very well drawn, but to demonstrate this, but in AC0, right, fan out is just it's not exactly an operation, but it's just the ability to take the result of any gate and feed it into future gates. So what this would look like is this AND gate at the end, say, could have as many wires coming out of it as we want. That's all I mean by fan out. Just copying.
So is it like cloning is not allowed? Is it some in some sense, is it cloning the output?
Right, it's cloning, but just classical information. So there's not any sort of no cloning theorem argument that kicks in for why it's not quantumly possible. We're just copying classical information. Does that make sense?
Yeah. Thank you.
Great. Right, and then we define the gate here as this gate that just copies classical information, but perhaps in superposition. Great. Okay. Okay. So, right. So sort of the first question Moore asked about this class QAC0 is whether or not it can implement fan out or parity. And so this would sort of mirror the celebrated result that classical AC0 could not compute parity or fan out. In fact, yeah, Moore conjectures that QAC0 cannot compute parity, just as in the classical case. And in the years since, there have been a lot of attempts listed here to show QAC0 lower bounds, but all of them sort of fall short of proving a fully general result. In particular, all of these results need to make some kind of assumption either about the depth of the circuit or about the number of ancillas used. So in particular, the state of the art is the lower bounds from earlier this year, or from last year rather, by Joshi, Tal, Vasconcelos, and Wright, where they show that depth 3 QAC0 circuits can't compute parity. And this other results from the year before showing that circuits with about linearly many ancilla can't compute parity. And so in some sense, these are a long way off in that, by definition, QAC0 circuits can have any polynomial number of ancilla qubits and any constant depth. But yeah, so that's sort of the current state of affairs with things on the lower bound front. But instead, sort of.
So what was the acronym? State of the art, is it? Okay, maybe okay. It's just state of the art. Okay, got it. Sorry.
Oh, sorry. So
that's
yeah,
just
yeah.
Okay, sorry.
Not the conference, yeah, or anything like that. Just
so the depth 3 result is with any number of ancillas, right? Like a polynomial number.
Right. And then the other result is for any depth, but with a.
I see. Yeah, because it's an unfair question, but like, do you know why it fails? Like, why can they use any ancillas at depth 3, but then they can't? I mean, is there a easy, simple explanation of that, or if not, it's okay.
I think it sort of boils down to some arguments about how much you could possibly entangle in depth 3 with these Toffoli gates. So these Toffoli gates are quite brittle in the sense that they do nothing if all of the inputs aren't set to 1. And so I think they're able to cleverly argue about how much they're able to entangle or influence in some fixed depth, sort of no matter how many you have. And then if you have a bounded number of ancillas, yeah, then they're able to argue that, okay, if the ancilla depth relationship is as shown here, then you're also not able to influence very much. But this is very hand wavy, so sorry about that.
No, yeah, it's okay. That's very good. Thanks.
Right. Okay. So so a lot of previous works have tried to show that QAC0 is weak by proving lower bounds, but instead we can ask, okay, what can QAC0 do? And this direction is quite a bit less explored. So in particular, even if QAC0 circuits can't compute parity, what sort of things could we hope to compute with them? And so the first known upper bound for any sort of QAC0 construction came from Rosenthal, where he shows that an exponential size QAC0 circuit can approximately compute parity on n bits. And this is a very nice construction, and it sort of mirrors the classical result that there does exist an exponential size AC0 circuit to compute parity. But it took quite a while to even show that this was possible quantumly.
So I guess the classical result doesn't imply the quantum result because of the fan out, right? That's I guess the central thing there. Okay.
Yeah, exactly. Yeah. So I guess one thing I'll mention along those lines is that in AC0 there always exists an exponential size circuit to compute any function you want.
Right.
Just because you could literally implement this. Yeah, the truth table. Yeah. But this requires exponential fan out, which we don't know how to do in QAC0, even in exponential size. So it is true to say that there exists a doubly exponential size QAC0 circuit to compute any function you want, but maybe not necessarily a singly exponential size one. Yeah. And so this result of Rosenthal is one of very few known upper bounds for this problem, or few known upper bounds in this model. And a more recent result shows that certain types of pseudo-random unitaries can be implemented in QAC0, but these are sort of more or less the only known upper bounds for QAC0. And as we were...
Can I ask another silly question? So here, have people looked at, okay, so we are saying, there's unbounded fan out, but if we look at, I don't know, bounded fan out, is that already included?
Right.
Or like, I don't know, like for example, if you're looking at an exponential size circuit, maybe allow polynomial sized fan out. Have people looked at these things? Is it obvious? Like, are there connections here? Or?
So if your AC0 circuit has, say, constant fan out, you can like just directly implement this in QAC0, right?
Yeah, exactly. Well, I meant more like in the bigger set. Like if you have exponential sized circuits and you have poly-sized fan out, does that help as opposed to not having any fan out?
Oh,
like
I mean this. Yeah, this lets you compute quite a bit. Like because of Rosenthal's construction, if you allow for exponential size, then you can implement polynomial size fan out gates.
I see. Okay.
And so you can compute a lot of things, but potentially not everything.
I see. Okay, thanks.
Yeah. Right. So I guess
so is that just to clarify? So is that a corollary that if you have exponential sized QAC0, then you can essentially apply poly-sized fan out? Is that like an intermediate lemma in the proof?
Yeah, I guess this is well, just because parity and fan out are
they're equivalent essentially. Yeah. Okay. Got it. Sorry. Thanks.
Yeah, good questions. Right. So this is, I guess, sort of what this final bullet point is getting to is that without these fan out gates sort of natively included in QAC0, it's unclear what we can compute or what we could even hope to compute. And so in particular, one sort of wild statement that still could be true, at least up up to now is QAC0 is strictly contained in AC0. And so this usually doesn't happen in complexity. You put a Q in front of the name of a complexity class, and it should be at least as strong as the classical thing. But at least in this case, this could still be the case, that QAC0 is strictly less powerful than AC0 for Boolean functions. And this sort of arises from this fan-out issue. Okay, so now I'm going to get into some of our results. And so first, what we show is that there exists a decision problem in QAC0 that is not in AC0 with mod p gates for any fixed prime p. And in particular, this shows that QAC0 is not contained in AC0p. AC0p, like I said, is what you get when you have AC0, and then you also allow for these mod p gates in constant depth. So AC0 p contains AC0, meaning that the statement I had on the previous slide actually just turns out to be false. So phew, that's a nice world we've avoided. And I guess I'll emphasize that prior to this work, the only Boolean functions which we knew how to compute in QAC0 were exactly those functions computable by AC0 circuits with constant fan-out. And so this is sort of an extremely limited class of Boolean functions. In particular, these are what are known as read K formulas for K is O of 1, which are sort of just guaranteed by the trivial simulation of AC0 with constant fan-out. And our second result is a bit more technical to state, so bear with me here. What the theorem says is that if f is some TC0 computable function, then there exists a constant c and a QAC0 circuit, Q of polynomial size, which computes this function fn up arrow n to the c. And it computes this function with completeness 1 and soundness 1 over 2 to the n. And so let me define what this up arrow notation is. So if we have some Boolean function that maps from n bits to 1 bit, then f up arrow k is going to be the function which takes in k many n-bit strings. And if all of these k n-bit strings are the same, then we just evaluate the function on one of the chunks. And otherwise, we just output 0. Is this clear? It's a bit notation heavy, but I hope the idea is simple. So we take like k blocks of n bits each, and if all of those k blocks are the same string, then we just evaluate the underlying function on say the first block. But if any of those blocks are different, then we just output 0. So okay, great.
And when you say completeness and soundness, I think that QAC0 can solve it, but what cannot solve it? AC0?
Oh
no, this is just the completeness and soundness is just to say that for any input, any input for which f is 1, the QAC0 circuit will always output 1. But if the value of the function is 0, it just outputs 0. It gets it wrong with probability at most 1 over 2 to the n.
Okay. So it's a yes and no instance thingy. Okay, got it.
Yeah. And I haven't defined TC0 yet, but it's just what you get when you take AC0 and also allow for gates that compute the majority function. And so this is a very strong class of classical circuits. In particular, they are strictly more powerful than this AC0p class for any prime p, which I defined on the previous slide. And this was proved sort of in a classic result by Razborov and Smolensky in 1993. And so Another way to sort of view this theorem from the previous slide is that QAC0 can compute any TC0 function with polynomially many copies of the input bits. So in particular here, I'm going to consider this exact n/2 function, which just outputs 1 if the Hamming weight of the input is exactly n/2, if the input is balanced, and 0 otherwise. And so what this is saying is that if you give me a bunch of copies of x, then I can compute this function. And so in particular, in the case of this exact n/2 function, it turns out that the number of copies we need is n squared. And for any other function computable in this TC0 class, what this theorem is saying is that there always exists some constant such that n to the c many copies of x suffice to compute that function in QAC0. Okay, so does this sort of notion of many copies make sense? It's a bit unusual, but it's what we're dealing with here. Okay, cool.
Sorry, I'm repeating the question by Atul, I guess, but what was the soundness condition in the previous slide? It's so completeness means that if the f outputs 1, then you can compute it correctly, and if it's 0, then with yeah, what does the 1/2 at the end means?
Right. So this is just to say that if I have some string that this function evaluates to 1 on, then our QAC0 circuit always matches that. It always outputs 1. But if I give you a string for which f evaluates to 0, then our QAC0 circuit gets it right with probability 1 minus 1/2.
I see. So is that what you call in the next slide the computing TC0 circuits? That this notion is like in the next slide you said QAC0 can compute any TC0 function. You mean it in the in the sense that with this completeness and soundness, right?
Yeah, in that sense, right,
Yeah.
right.
Oh, okay, got it. Yeah.
And so, okay, maybe you would like for there to be perfect completeness and perfect soundness, but I don't know. Usually when we define these classes, like BQP, for instance, 2/3 and 1/3 are sufficient. So I don't know. Take that as you will, I guess.
I mean, this is what you just need to prove your result, so it makes sense.
Yeah. Yeah. So I guess something I'd like to sort of, I guess, emphasize here is that
sorry. Before you go on, since you already asked, interrupted, I also wanted to check. So this result by Rosenthal that you mentioned.
Oh, yeah.
So there also it was approximate, right? Like you're computing parity approximately. Was it also in the same sense that it was inverse exponentially incorrect? Yeah. Okay. So we
although his right, so his construction will have errors on both sides. So
so here you have perfect completeness, but he also had like inverse exponential completeness error. Is that?
Yeah.
Okay. Got it. Thank you.
Okay. Yeah. So something I'd like to emphasize is that this notion of many copies is sort of like a uniquely quantum phenomenon, in the sense that classically having many copies of your input is really not helpful in any meaningful way. So in particular,
I have one very, very dumb basic question. So if you're able to get completeness to be 1, like so if on yes instances, so suppose I have a function f and I define a function f with which negates the output, right? And you're saying you can get completeness right for both of them, is it? So because if f is TC0 computable, I'm sure negation of f is also TC0 computable. So shouldn't you be able to combine them to get both perfect completeness and perfect soundness?
That's a good question.
Because normally the issue is that there are promise problems and you can't flip, all these kinds of things. But if it's a Boolean function,
that is a very good. So
I'm sure I'm saying something wrong, but I just don't know what I'm saying wrong. That's why I'm asking.
No. That's a good observation. But it turns out that right. So okay. So the thing you said about like negating all of the input bits, the instances that we get. Okay. So we're not talking about like the underlying TC0 function here. We're talking about this like transformed function with this copying business. And so if you negate the input bits to this function, whatever you started with will also be a no instance of any other of these like copy functions. So in particular, like if all of your blocks aren't the same, so like these are the instances that we actually maybe I'll save this for later, but it's a good point. Yeah. Sorry,
no, it makes sense. Yeah, please carry on. We can discuss later. Thank you.
Yeah. Right. Okay. So. Okay. So.
Question. So, in your result, does the constant C depends on the type of function, or is just a fixed constant, something 2 or 3?
Oh no, that's a great question. So this constant is going to depend on. So for simple functions like parity or majority, it's always going to be like 2 or 3 or something like that. But for right, so this result applies to any TC0 function, and the constant here is going to depend on the size of the TC0 circuit that computes that function.
I see.
Yeah, or the size and the depth, but it will always be a constant.
Yeah, makes sense.
Yeah. Okay, so one thing I'd like to emphasize is that this classical copies thing is sort of useless in the classical setting in the following sense. Suppose you have some classical circuit, let's just say it's an AC0 circuit consisting of AND and OR gates, that computes this like sort of K block version of F. And so as you can see on the left here, we have the first K bits, which are all X1, the next K bits, which are all X2, all the way to K copies of Xn. And so we have the circuit that computes F up arrow K. However, I claim that if you had such a circuit to compute F up arrow K, then it would also be pretty easy to get a circuit that computes just F itself. So in particular, what you could do is you start with your inputs X1 through Xn, and then you just fan them out K times. So now you have K copies of your original input, at which point you could just run the circuit that you had before that computed this F up arrow K function. And so the claim is that now this new circuit just computes the original underlying function F. And this is possible because of classical fan-out. And so if K is a polynomial, then the size of this new circuit C is just going to incur, the size of this new circuit C prime is just going to have some additional polynomial overhead on top of the size of this other circuit we had. And so maybe this didn't make sense, but all I'm trying to say is that F up arrow K and F have the same classical complexity up to polynomial factors for sort of any model of interest, at least in this constant depth regime. And so this is a bit strange, only because we're able to compute very hard functions quantumly once we have many copies of the input. So to illustrate this point, let me just say F is this exact n/2 function. We know that exact n/2 is hard for AC0P circuits, for example. Any AC0P circuit computing this function must have exponential size. And based on what I just said about this classical copying business, the complexity of exact up arrow n squared n/2 is also going to require exponential size circuits just via this reduction. However, from the slide before that, we know that exact up arrow n squared is computable in AC0, or QAC0 rather. And so this gives us the separation, and I think hopefully demonstrates this point that I was trying to get at, which is that classical copies are sort of useless if you have a classical circuit, but once you have a QAC0 circuit, having classical copies can in fact help. And in particular, this gives us this sort of clean separation. QAC0 is not contained in AC0P. Okay, so I just said a bunch of stuff. Does this slide make sense? Okay, great. So now I'll get on to actually talk about some of the techniques that we ended up using to prove this result. And the first of which is this method of so-called precise amplitude amplification, which this slide's going to be very technical, but the idea is very easy, and I think you'll probably see how it works rather quickly. And so we start with this question, which is, okay, what states can we prepare in QAC0? Earlier, we were concerned with which sorts of Boolean functions can be computed by QAC0 circuits. But now we're going to ask, okay, which sorts of quantum states can we prepare with these circuits?
So before you start, maybe I can ask a small question. So that's okay. So when you define this F up arrow thingy, if instead of saying 0 on other inputs when the blocks don't match, if you put 1, then completeness and soundness would have flipped, right? Is that correct?
Let's see. I think if you do that, you also need to flip F, right?
You have to like put F bar or something instead.
Yeah. But it'll, I think, like morally still be the same object.
Okay. Thanks.
Yeah. Yeah, this notion, this like F up arrow thing seems a bit unnatural, but I hope by the end it starts to make more sense. Okay, so right. So we're interested in states now. And so what I'm going to say is, suppose psi is some state that has a nice structure. In particular, let's suppose psi is just a uniform superposition over the one inputs of some Boolean function. And further, suppose this Boolean function is computable in QAC0. And also suppose we have some state phi, which is supported well on psi, sort of in the right way. In particular, we can write it of this form, as square root c plus psi plus square root 1 minus c psi perp, where psi perp is going to be like unsupported on any of the relevant basis states. Then what I claim we can do is we can extract out the desirable part of the state phi. And so what I mean by that is, since the state is of this very nice form, where it's a uniform superposition over the one inputs of a function that we know how to compute, this function f, then what we can do is we can prepare our state phi, and then tack on an additional ancilla qubit, and then just compute this function f coherently. And what this does is we get a 1 on the part of the state that corresponded to f, aka psi, and we get a 0 on the rest of the state. And the point is now, maybe you're seeing this, is that if we were to measure that last qubit and post-select on it being 1, then the state we'd be left with is exactly psi. And so this is sort of the first step of this precise amplitude amplification protocol.
So in the second step, you've already applied UF, right?
With phi here, this.
Yeah, in the first equality on the right, like in the middle term, you already applied UF, right?
Yeah, sorry about that. That's a typo. Those should both be zeros.
Yeah. Okay. I got it. Yeah. Okay.
Yeah. Those should both be zeros. And then maybe
the amplitude.
maybe just ignore that middle expression.
Yeah.
Okay, so right. So after we apply this UF unitary, we can also apply maybe an X and a Z on the last qubit to end up with a state that looks like this, which isn't too dissimilar from what we had before. Now the point is that we had this state phi from earlier, which sort of acts as like an initial approximation of our state psi, with C being sort of the measure of how good that approximation is. And what I'm claiming is that by sort of toggling the phase on this ancilla qubit, that's either is 1 in the psi branch and 0 in the psi perp branch. This operation acts sort of analogously to the oracle in Grover's algorithm. And this initial approximation state, I claim that reflecting about that is analogous to the diffusion operator in Grover's search. And so this isn't too crazy, I don't think. This is sort of along the lines of any amplitude amplification variant you've seen before, but just to make everything complete here, we can alternate between these diffusion and oracle calls, and eventually we'll end up with some state that's very close to the target psi. And in particular, the math works out such that if C, the initial sort of approximation factor, is equal to the sine of pi over 4k plus 2, then after k iterations of this amplification procedure, we will exactly end up with the state that we wanted, psi. And so what this means is that if C was some constant in the first place, then k is also going to be a constant, and this whole procedure will have been possible in constant depth, assuming those unitaries sort of corresponding to the oracle and the diffusion operator were implementable in constant depth. Right. So so all this to say, we have some sort of limited version of amplitude amplification that we can do in QAC0. And one sort of nice corollary of this is that we can make constructions from prior works that incurred some approximation error. We can make those exact now. And so in particular, this construction of Rosenthal, maybe don't worry too much about what this exact state is. In this construction of Rosenthal, he's able to approximately prepare an n-qubit GHZ state. In particular, the state is going to have like some inverse exponential amount of overlap with garbage. There's going to be some sort of additional garbage term hanging off. But the nice thing about the GHZ state is that the sort of relevant part of it, or the basis states that we're interested in, correspond to a very simple Boolean function, which is this function that only accepts the all 0 string and the all 1 string. And so if I go back a second here, then psi just becomes the superposition over 1 inputs of this very simple function. And Rosenthal's construction gives us exactly this phi that we were interested in. And we can apply this flagging based on this Boolean function that only accepts 1 to the n and 0 to the n. And so all this to say that we can exactly prepare an n-qubit GHZ state in QAC0, but the circuit still has to be exponential size. But at least we're able to remove the approximation error. And so one sort of nice corollary of this is that if we shrink the entire construction down such that the target, the GHZ state we're trying to prepare, is on like log n many qubits, then the size of the circuit is going to be exponential in log n, but exponential in log n is just polynomial. And so what we get is a polynomial-size QAC0 circuit to exactly prepare GHZ states on log n qubits. And so now back to this question of which sorts of Boolean functions can we compute in QAC0?
Sorry, the previous thing that you mentioned seemed very interesting. That you can implement log-sized. So you can prepare log-sized fan out as well. Yeah, okay, they're equivalent. I always forget in my head. So you can prepare. You can do log-sized fan outs. Are there like immediate consequences of that we know of? Does it like immediately give us something nice? Having
yes.
log-sized fan outs.
Right. So what this should immediately give you is that you can compute the parity of log n bits, and then via I don't want to go back all these slides, but there's this result of Hoyer and Spalek showing that with fan out you can compute like a majority or the QFT or stuff like these hard operations.
You can do all of them for log n. Yeah. Okay.
Yeah. Exactly.
But from the impossibility side, do we know that we cannot Can we compute parity for log n bits using AC0?
Yeah. So you can just do this.
Oh yeah, it's just the reverse amplification thingy, right? Like it's an exponential size relative to the number of inputs. So I guess the truth table thing. Yeah. Okay. Sorry. Okay. Thanks.
Yeah. But here are some not so immediate consequences of this fact. I claim that there's like an interesting class of Boolean functions on n bits that we can now compute with log size fan out gates. So let me just remind you that these threshold functions are defined as follows, where we take in n bits of input and output 1 if the sum of the bits is above some threshold. And then these exact threshold functions, exact k, are defined similarly, but it's like only outputting a 1 when we exactly hit that threshold. And so there's this classic work from the 90s showing that if you have k equals like polylog n, then these functions are computable in AC0. And moreover, they're computable with an AC0 circuit that only has log fan out. And so what this means is we can use this construction from the previous slide, this sort of refining of Rosenthal's construction, to implement log size fan out gates. And from there, we can directly simulate this construction of these AC0 circuits. I believe this paper is by Haustad, Worm, Wegener, and Yu from 1994. And so we can just directly implement their construction. And it turns out that every symmetric function computable in AC0 admits a circuit like this that only requires log size fan out gates. And so as a consequence, we get that the set of symmetric functions computable in AC0 is also computable in QAC0. And so this is okay. So now we've made some progress on the question of what functions QAC0 can compute. But further, I'm going to claim that we can go back again, right? Okay, so we started with this question of which Boolean functions can QAC0 can compute, and then we tried to look at which states QAC0 can prepare, and then we made some progress there and found this larger class of functions that QAC0 can compute. Now we're going to go back to the state picture and ask if these new Boolean functions we have can be leveraged to prepare more interesting states. Right. Okay. So the whole thing with this precise amplitude amplification procedure was that we were able to use some Boolean function to, in some sense, flag or tag an interesting state, and then amplify from there. But now we have more functions at our disposal. So perhaps one may get the idea to apply this again. With these new functions. In particular, our target is going to be this state, the W state, which many of you may have seen before. But if you haven't, this is this state which is uniform superposition over strings of Hamming weight 1. And so I think physicists care about this state because it's symmetric and has nice entanglement properties. But for us, it's interesting because it can be written in the following form. We can write the W state as a uniform superposition over the 1 inputs of this exact threshold function, exact 1. And what this means is that if we can get some sort of initial approximation of this W state, then we can apply this exact 1 function in order to sort of tag the relevant part, and then proceed with our amplitude amplification procedure. I claim that this W state admits an easy to prepare approximation. In particular, the W state is well approximated by some product state, this thing I have written here, sigma. And so what we can do is we can prepare this product state in QAC0, and then we can apply this unitary that computes the exact 1 function, because this is exactly one of these functions guaranteed by the previous lemma. And so from here, we can exactly prepare the W state by a polynomial-size QAC0 circuit. And okay, the W state is not just an interesting state from a physical perspective. I'm going to now show that this state is useful for computing even harder Boolean functions, even more interesting Boolean functions.
So just to make sure I'm following things, so we haven't yet proved the main result, right? Like the one that you said that TC0 functions can be computed with some. We are building towards it, right? I didn't miss it.
Yeah, we're almost there. We're almost there.
Okay, nice.
Yeah. Okay, so before I get to saying what the W state is useful for, I would like to just go back to this theorem of Moore, where he shows that computing parity and preparing the cat state in particular are equivalent. And so how this reduction works is pretty simple. It's the following circuit. So if U here is a unitary that prepares the n-qubit GHZ state, then this circuit, I claim, exactly computes the parity function. I'm not going to go through a proof of why this works, but what I am going to claim is that if U instead, and then this is what the circuit does. It computes the parity of these n input qubits. What I'm instead going to claim is that if U prepares the W state instead of the cat state here, and we plug this in, then the resulting circuit is going to do something interesting. In particular, it's going to compute some Boolean function. And this is what we call the W test. And so the claim is that being able to prepare the W state allows us to, in some sense, weakly compute this exact n/2 function from earlier. Right, so we have this Moore circuit again, except now the unitary U maps the 𝖢0 state to the W state. And the whole thing is a QAC0 circuit, just because this W state implementation was constant depth, and the CZs are a single layer, and this OR gate is a single layer. Right, okay. So what happens when we apply this circuit? So initially we're just going to map our ancillas that are set to 𝖢0 to the W state. So we have X, W, and then 0 on this final wire. And then what we're going to do is we're going to apply a controlled Z gate between the first qubit of X and the first qubit of this W state, and then the second qubit of X and the second qubit of this W state, and so on. And we're going to do this for every bit of input. And what's going to happen is we're going to add a phase to the sort of ith component of this W state, or this EI basis state, according to whether or not Xi was set to 1. So if Xi is set to 0, then of course the CZ gate won't fire. But if Xi is set to 1, then we're going to pick up a phase exactly on this branch where the ith bit of the W state is 1. And I'm going to denote this state with these phases now as WX. And finally, we're going to apply the inverse W state preparer, and we're going to be left with the state which is like X 𝖢0 𝖭𝑥0. And finally, we're gonna take an OR over all of these n qubits corresponding to 𝖢0 𝖭𝑥. And so what this means is that we're going to flip this final qubit on this last wire if and only if the ancillas are not all zeros. Right. This is how the OR function works. It just maps anything that's not all 0 to 1.
Okay, so this is me being like a compiler and getting a little bit lost in the formula. So at the bottom formula, shouldn't there be like a 0 on the left hand side as well?
Oh yeah, sorry about that. Yeah.
Okay. Just checking. So the W sub X is basically the thing with the superposition, right?
Yeah.
Okay, good.
Yeah. Right. So yeah, so we have this XWX, and then we apply 𝖢0. And then what we're doing in this last layer is we're just checking if 𝖢0 mapped WX back to 0 or not with this OR gate. And so in particular, if the input X is all zeros, then none of these phases are going to appear. And we just have the W state as we did originally. And so applying 𝖢0 is going to map it exactly back to 0. But this is, of course, not always going to be the case. And so, okay, so what I said earlier is that this OR gate flips the final qubit if some qubit in these ancillas is not set to 0. And so we can just exactly compute this probability as follows. We just look at the amplitude on 0 of this 𝖢0 WX state and square it. And what we get by applying 𝖢0 backwards is just the inner product between W and WX. And we can sum all of these up, and what we find is this probability is going to be equal to n minus 2 times the Hamming weight of x divided by n all squared. So it's some quadratic function drawn on the left here, depending on the Hamming weight of x. And so one interesting thing to note is that this function is exactly equal to 0. It has a unique root at x equals n over 2. Hamming weight of x is n over 2. And otherwise, I claim that this probability is going to be at least 1 over n squared. This is just because if the Hamming weight of x is an integer value, and so if you're at n over 2 and you jump up 1, then the sort of numerator in this probability is going to be some constant, at least. And so you're going to get at least 1 over n squared or something like that, probability of measuring 1. And so now the point is this circuit is sort of going to deterministically output 1 if the Hamming weight of x is n over 2, just because this probability is exactly 0 there. And otherwise, if the Hamming weight of x is not n over 2, we're going to have at least a 1 over n squared probability of outputting the correct answer. So in some sense, you can think of this W test as computing exact n over 2 with perfect completeness and soundness, roughly 1 minus 1 over n squared. And so this is sort of the real subroutine powering our results. Does this make sense?
Right. So here n is the number of right. Sorry. Yeah, I thought I had a question. I don't. Sorry.
Good. Yeah. So right. So this is getting toward the main result, but the soundness is still quite bad. And so now I'll sort of describe how this figures into the theorems I mentioned earlier. what we can do is if we could run the W test t many times in parallel, and then just took like the AND of all of those results, then we could boost the soundness from what it was, 1 minus 1 over n squared, to 1 minus 1 over n squared to the t. However, we can't run the W test in parallel if we don't have many copies of the input in the first place. Because, right, we need to do this step of the circuit where we entangle X with the W state, with these CZ gates. And so without many copies of X, we can't do this. And without fan out, we can't make many copies of X. But what we can do is we can make use of copies that are given to us. So if we start with a bunch of copies of X on our input register, then for each of them, we can in parallel implement this W test. And so what I mean is that we can implement the following transformation. Okay, yeah, I guess this is a bit imprecise because the left-hand side should have some additional ancillas, but you sort of get the idea, is that without, with many copies of X, we can produce many copies of WX. Just because doing it once is a QAC 0 operation, and this parallelizes sort of trivially. And so what this means is that we can compute this exact n/2 function with super high precision, given like n cubed copies of the input bits. And so this is what leads to our main result. And I guess I'll just mention that the result follows because once you can compute exact n/2, from there you can build a TC0 circuit. So the definition of TC0 that's sort of more common is that you can have majority gates in your circuit, but the definition of TC0 doesn't change if instead of majority you say exact n/2, this exact threshold function. And so what this means is if we're given some TC0 circuit, what we can do is we can set up these W tests to compute exact n/2 whenever we need to, and then with sufficiently many copies of the input bits, we can compute exact n/2 with high precision, and then feed this forward in our simulation. And this is what lets us compute any of these threshold functions, or sorry, any of these TC0 functions with sufficiently many copies of the input bits.
Right, but with so if you have these two definitions that you're saying that they're equivalent, right? Is it the case that so to show equivalence, you're using some underlying class, I'm guessing, right? Like I know the AC0 or whatever, I know NC0 equivalent, but I'm wondering if in the reduction we use fan out anywhere.
Oh yeah, so in the reduction,
yeah,
in the reduction we do use fan out. That's a really good observation. Right. So if you wanted to implement majority using exact n/2 gates, I think something that's like roughly optimal is you could sort of like offset your n/2 gate by like padding. And so to compute majority, you like check exact n/2 or exact n/2 plus 1 and so on.
I see.
But doing this is going to require huge fan out, as you observed. But this sort of isn't an issue for us in this like many copies regime, because every time you need classical fan out, you can just like request more copies of the input.
Right.
And so this just results in a polynomial blow up in the number of copies that you need.
I see. No, because I was trying to see if your result, so there is a version of your result that works with a single copy, right? So I'm guessing you need many copies because you're running the W test in parallel. Is that correct, or did I miss something in the agreement somewhere?
Right.
So I'm guessing you lose some soundness, right, if you have just one copy. But I was just trying to see what the statement would be with a single copy.
Oh. Right. So the statement with a single copy is this like 1 over n squared versus this like 1 over n squared, 1 minus 1 over n squared soundness and perfect completeness. But this thing earlier where I defined this like f up arrow function, in that case we're only getting one copy of the input bits. But what we can do is we can check in QAC 0 if it's of the right form. Like we can do an equality check on like each of the different blocks. And then after having done that, we essentially have like n squared copies of the input bits. Like
Oh.
of this, like there's this underlying block that that the big thing should consist of. And then once we check it's of that form, then we can run our parallel tests.
Yes. Thank you.
Yeah, so this is I guess the last of the technical stuff. I have a couple of open questions I can mention, and then we can talk some more. Okay, yeah, so the first question is whether or not this like soundness error can be eliminated. In the way that we're doing it with this W test, we are always going to have some amount of soundness error. Seems like some kind of very, very new approach is going to be needed to get around this, if it's possible, but I'm not sure if it is. Second is a question that we didn't really touch on much, but it's this question of whether or not AC0 is contained in QAC0. So what we showed here is that QAC0 is not contained in AC0, but we have sort of said nothing about the complexity of AC0 functions for QAC0. And one sort of interesting example is this this indexing function. So this indexing function is the function that takes n bits of like data bits and then log n bits, which correspond to some index, and you're required to output the value of x at that index. But what we can show is that computing this function in AC0 requires large fan-out classically. So it requires fan-out that's like polynomial in n. And so I think it's a really interesting question. If this function could be computed in QAC0, how could we get around this need for large classical fan-out? I think that's a really nice open question. And the indexing function is like somewhat exemplary of a hard AC0 function, sort of in the sense that it needs large fan-out. And then, okay, here is another open question that's, so like I mentioned, we can't make copies of the input without fan-out. We can't make many copies without fan-out. However, we are able to achieve some amount of parallel repetition via other means. So this is in one of the appendices of our paper, where we show that you actually can run the W test n times in parallel with just a single copy of like an n-bit input string x. And this is a bit of an involved construction, but I was lying earlier when I said that we can't achieve any sort of parallelization with a single copy. We can, but only up to n copies. And sort of this isn't sufficient to actually compute the function with just a single copy of input, but it is enough to drive the soundness error to like 1 minus 1 over n or something like that. And indeed, if you could go from n here to like n squared, then you would have shown that QAC0 can compute parity. And so this is I think a really interesting direction, is to what extent can the parallel repetition we achieve be boosted, to some better polynomial, and maybe even hopefully to n squared. And then the final question is, can QAC0 compute parity? So I think the previous open question is maybe one sort of route toward proving that the answer is yes. I don't really have any leads on proving that the answer is no, but yeah, I think this is an interesting question.